Chapter 2.4 talks about the periodic table and the history of it and how it was developed. And it's really essential. It's really simple to get the information because overall the history of the periodic table, it hasn't changed a whole lot. After Dalton started doing his atomic development of theory, there was a lot of experimentation that started taking place. That was the main starting point. In 1869, a Russian chemist named Dmitry Mendeleev created a periodic table that was useful for all chemists. Now, Mendeleev, a little background on him, was a Russian chemist. He grew up in Siberia, and his father was a chemist for the state or the Russian government. And Siberia is a very desolate place out in the middle of nowhere. And Mendeleev grew up with his father in the lab, spending a lot of time. So he spent many days, many hours as a child working on chemistry. He decided it was a good way he wanted to develop a table of some sort, a way to organize the elements, to put them in order of some way to make it useful for all chemists. And at that time, there were only 68 elements that existed. He took the 68 elements, and what he did was he arranged them according to atomic mass. He took all their masses, which were known at the time, and he arranged them in order. So on a card, he would take everything he knew, what it reacted with, its density, what it looked like, what other properties it may have had, physical and chemical. When he laid them out in order, he noticed that every eighth card started repeating a pattern, that the ninth card was similar to the first card. So what he decided to do was take the elements that were similar in properties and line them up underneath one another to get things to match up. And after doing this, he ended up predicting that there were actually some elements that were not yet discovered. One of the most famous ones he predicted was germanium, which he called ecosilicon, and he predicted it about 15 years before it was actually found or discovered on the Earth. And a lot of the properties he gave were very similar to what they were when it was actually discovered. It's believed there was another chemist named Lothar Meyer, who was a German chemist, who was also working on a periodic table very similar to Mendeleev at the same time. And actually, it's believed that he created his first, but because Mendeleev published first, he's the first person to get credit. Mendeleev knew there were inconsistencies in his periodic table. He knew that it wasn't perfect. But it was very good the way it was. So in 1869, that was first created. Henry Moseley then came along in the mid-1900s, early 1900s, and as a result of using X-ray diffraction, which is the process of X-raying an element and looking at peaks that were generated, he found that very specific pattern showed up, and that pattern was later associated with what we call the atomic number. It was a way of determining the number of protons in an atom that we talked about in the past. Based on these new atomic numbers, Mendeleev rearranged the periodic table by increasing atomic number instead of atomic mass. When he did this, all the inconsistencies that existed in Mendeleev, or the few inconsistencies that existed, disappeared, and they were no longer there. So if the elements were arranged by periodic table by atomic number, all the patterns started becoming clear, and there are many patterns that exist. First off, the vertical columns now lined up perfectly, and these families or groups were given that name because they're very much like members of a family. Much like you are similar in properties to the members of your family, you're not identical, you have similar properties. So the members in a column or a group are similar to one another. So for example, all the elements in lithium, sodium, potassium, rubidium, cesium, and francium are similar to one another. Sodium is most similar to the ones that are adjacent to it, lithium and potassium, and that's true of all elements in the periodic table. They are the most similar to the elements that are closest to it vertically up and down. Some of the families we've given names to, and you are responsible for these names, and I have given on your periodic table the Roman numeral. In the periodic table, group 1A, which ranges from hydrogen, lithium, sodium, potassium, rubidium, and cesium and francium, are referred to as the alkali metals. The alkali metals are very reactive metals. They will react in water. Francium is so reactive that it's not found in nature by itself. It cannot exist in nature. Cesium is extremely reactive, and a chunk of pure cesium when thrown into water will explode. If we throw a piece the size of a nickel in the size of a bathtub, it would blow the bathroom apart, or the whole tub apart as well. The second family we look at is the alkaline earth metals, and they are from beryllium down through radium. They are reactive, but not quite as reactive. Again, the properties are similar to one another. The center section of the periodic table, ranging from scandium over through zinc down through mercury in this general section here, the sunken section, are called the transition metals. And they're called transition metals because they can transition in charge. They can change a charge from one form to another. We'll talk more about that at a later date. It also continues a little bit over down this area from gallium to indium and tin, and thallium and lead and bismuth. Those are also considered to be transition metals at time, but they're not the purest transition metals. As we move over, the families underneath boron and aluminum have no family names because it's only those two. Carbon has no name, nitrogen has no name. Oxygen family underneath, from oxygen down through polonium, are called the chalcogens. Fluorine down through astatine are called the halogens. And that word should sound familiar to you because halogen light bulbs are the newest rave. They have gases of those elements in the light bulbs, which are low energy, and they produce a very bright light when they are given electricity to throw through them. The last column on the periodic table are called the noble gases. They used to be called the inert gases because it was believed that they would not react at all. But we now know that those elements will react under high pressure, so we changed that to noble gases. All right, so vertically there are similarities. Horizontally in the rows are called periods, and a period has no similar properties. As we go across the rows, there are no similarities in these elements. Now, one of the other benefits that was generated out of the periodic table, which becomes extremely useful to us as we move on later into this chapter and into the remaining chapters of the year, are that we can see that the metals, the nonmetals, and the metalloids are divided very evenly by the boron staircase. On your periodic table, the boron staircase is this bold blue line that zigzags its way down through the elements. The boron staircase is a demarcation line. The elements along that line are all considered to be metalloids. So, for example, if I looked at boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine, those are considered to be metalloids. A metalloid is an element that's not truly a metal, not truly a nonmetal, it's sort of in between. Now, if you'll notice, the elements that are on that line have a side in common, so not the point. So, for example, if you notice when it's cleared away that phosphorus might have a corner on the line, but it's not a full side, therefore it is not considered to be a metalloid. The only thing along the boron staircase does not fit this trend is aluminum. Aluminum truly is a metal, so that is one exception to the metalloids. Everything to the left of the boron staircase, including aluminum, so everything to the left of that and down, all this part over here, are considered to be metals. As you can see, the majority of the elements on the periodic table are metals. On the periodic table, we can also see some colors. Your periodic table has 3 different colors of element symbols. Blue indicates that it exists naturally at room temperature in a liquid state. Black means it exists naturally as a solid at room temperature, and red means it exists naturally as a gas at room temperature. The outlined ones like technetium, promethium, neptunium, and all those, the outline format simply means they are radioactive and man-made. Those elements we will talk about a little bit later. You're responsible for knowing names and symbols for the elements in the upper body of the periodic table. So at any given time on the final or in the test, it is expected of you to know that rhodium, palladium, and silver are RH, PD, and AG correspondingly, for example. Or vice versa. If you're given a symbol, it is expected that you know the name, and that would be expected of you as you move forward. So you do, even though in this online course we don't need that, you're responsible for those. The nonmetals then are the remaining components, the upper right-hand corner of the periodic table. So everything above and to the right is considered to be a nonmetal. Again, hydrogen is truly a nonmetal. Even notice on the left side, it fits over here. Chemically speaking, hydrogen fits above that first family better than any of the other families. That's why it is placed there. All right, so the history of the periodic table we've developed here, and we've talked about some of the layout of the periodic table, which is essential. You should be able to look at the periodic table and tell whether something is a metal, nonmetal, or a metalloid. And with metals, nonmetals, and metalloids, that becomes essential throughout. You also should be able to look at any element on a periodic table and tell what family it belongs to, so you're responsible for those things.